Welcome to the course on Design and Analysis of Algorithms. Our topic for today is Combinatorial Search and Optimization. The general problem that we are going to address is something like the following. So we want to find an object and this will usually be a discrete object, say a set of numbers or a graph. And since it's a discrete object, when we talk about a set of numbers, we will usually mean a set of integers or even perhaps set of 0, 1 values. And this object must satisfy certain given constraints. So find an object such that first it satisfies some given constraints. Okay. And furthermore, optionally, there might be a second requirement that of all objects satisfying those constraints, we want an object, say, of the least cost. Where the cost is a function defined on the objects, is a function from the space of objects to say real numbers. Optionally, we might also have an alternate definition in which instead of saying we want least cost, okay, so option 2, it could be stated differently. Instead of asking for the object of least cost, we want an object of maximum benefit. Find object of maximum benefit, of course, in addition to satisfying the given constraints. Benefit is also a function from the objects to real numbers. Okay. You may note immediately that these are not really two distinct formulations, but we can set benefit equal to negative of the cost, and then instead of maximizing the benefit, it's the same as minimizing the cost. So this is an abstract definition, and let me give you a few examples immediately. So let me first start with a familiar example in which there is no objective function given. Okay. So this cost function, for example, or this benefit function is also often called objective function. And so in this first example, we are not given an objective function, but we are only given constraints. Okay. So this example that I am going to talk about is the so-called 8 queens problem. Probably most of you know what this is. So we are given a usual chessboard, and we want to place queens on it. So place 8 queens on usual, which is an 8 by 8 chessboard, such that no two queens capture each other, or no two queens are in the same row. Same column or same diagonal. You may wonder why this is a problem in the sense we have described. Well, we can always model it as a problem on numbers, on integers. So we can think of this as find Q1, Q2 to Q8. Okay. Let's say Qi represents where in column I the ith queen is going to be placed. Okay. So find these Qs such that Q of I is not equal to Q of j. Okay. So interpret Q of I as equal to the row in which the queen in column I is placed. Okay, so this condition simply says that the queen which gets placed in column I, okay, does not have as its row number a value which is the same as the value which the queen in the jth column is placed. So in other words, the ith queen and the jth queen are not placed in the same row, and we will assume that the ith queen is placed in the ith column and the jth queen is placed in the jth column. But this is not all. Okay, so we have already taken care of the first condition, that they are not placed in the same row. Well, they are not placed in the same column because we are only defining 8 variables, and we are saying that Q of I is the position of the queen which is going to be fixed in the ith, which is going to be placed in the ith column, and we are only giving the row. Now we need to take care of the condition that they are not placed in the same diagonal, and this condition is easily taken care of by asserting that, say, Q of I minus Q of j. Okay. This is simply the distance along the rows, okay, or the vertical distance. The distance between the rows. And if I take the absolute value, it will actually be an unsigned distance, and this should not be equal to I minus j. Okay, so this is true for all ij distinct. So we have now formulated the 8 queens problem as the problem of finding a sequence of numbers Q1 through Q8 such that they satisfy these 2 conditions. Well, actually these are not 2 conditions, but these are conditions which apply for all I and j. So this is, say, whatever, 8 times 8 upon 2 conditions. This is also 8 times 8 upon 2 conditions. Of course, this is really a toy or a game problem, but we can have more serious problems as well. So let me give a few of those. The second problem that we are going to look at is the so-called knapsack problem. In this case, in fact, we are going to have an objective function as well. So in this case, our question was, do there exist such numbers, okay, that satisfy these conditions? But we did not say that if there are several such 8 tuples of numbers, which one are we interested in? We said that just find any such set, okay, or any such sequence really. Here, we are also going to have an objective function. Okay. So here we are going to have an input, and the input consists of, say, numbers v1, v2 all the way till vn, and think of vi as the value in rupees, say, of ith object. Okay. So implicit is that there is a set of n objects over here. Each object has a value, and that value is known to us. In addition, each object also has a weight. So say w1, w2 all the way till wn, and say such that wi is the weight, say in kilograms, of the ith object. And imagine that we are given a knapsack which has capacity C. Okay, so C is weight capacity by weight. The problem should be obvious by now. We want to determine which of these objects we should place in the knapsack such that we don't exceed the capacity of the knapsack and such that we are picking up objects of maximum value. So we want to find a subset of the objects such that value of objects, the total value of selected objects is as large as possible, while total weight is less than or equal to C. Okay. So, although this problem looks like it arises in the context of objects and values and weights, it can also arise in other contexts. So, maybe there are jobs and there are profits associated with the jobs, and we want to decide which jobs to select or something like that. So, again there is a constraint over here. Well, first of all, there is a combinatorial object that we need to pick, which is the subset of the given objects, or perhaps you could call these objects items. So, we want to pick a subset of these given items, and there is a constraint on them that the weights of the selected items should not be bigger than C. That is the constraint. And then there is also an objective function. The objective function is that their value should be as large as possible. So, this is a maximization problem. And the objective function given to us can be thought of as a benefit function, because after all, if we pick as many objects of large value, we are maximizing the benefit to ourselves. Let me give you one more example. This is another classic example. This is the so-called traveling salesperson problem. The input over here is a graph, is a weighted graph. And the output is a tour through the graph. That visits every vertex exactly once, and the objective, we want to minimize the weight of the edges in the tour. The name comes from the association that you can think of this weighted graph as representing a map of a city, for example. A map of a country or a map of the world. Vertices represent towns and edges represent roads, and the weights represent the length of the edges. So, imagine that there is a salesperson who wants to visit every city for selling his products. However, he wants to make sure that he travels as little as possible. So, this is a problem that he or she might want to solve. Okay. So, he would like to find a tour that visits every city exactly once, such that the total distance covered along all the edges is as small as possible. Again, on one hand, this may seem like a problem relating to salespersons and cities and roads, but this problem arises in many contexts. For example, this problem arises in robotics, this problem arises in computational biology, and many other fields. Before carrying on, let me give you an example of this problem, just to clarify what is meant over here. So let's say that we have 4 cities. Okay, these are our 4 cities, and so this is our graph. So typically, we will have a complete graph over here. The graph I am going to draw is going to be an undirected graph, but this problem makes sense in the directed case as well. Okay, so this is the graph, and let's say there are weights over here. So for example, this weight could be 1, this could be 2, say 9, this could be 6, this could be 2, and say this could be 4. So there are various ways in which the salesman could tour through these cities. And so for example, one way is this outer tour. What is the cost of that? Well, the cost of that is 1 plus 2 plus 9 plus 4. So that is 16. Okay. Here is a better tour. Okay. So for example, something like this. Okay, so this figure of 8, this tour. Okay, what's the cost of that? That is 2 plus 6 plus 2 plus 4. Okay, so that is 14. So this is in fact a better tour than just the outer tour. And in fact, you should be able to check that this is the best possible tour. In any case, the point is we want to make sure that we have found the tour which has the minimum such cost, or the minimum such length, if you like. These are only 3 examples of the kinds of problems you have in mind. And in fact, later on in the course, we will be considering more problems of a similar kind. But let me now state the topic for today. The idea today is to look at, we want to start a study, okay, of strategies for solving combinatorial optimization problems. Combinatorial optimization and search problems. I may drop the search occasionally, but that's implied. Today I want to talk about a few basic strategies. One is based on the so-called backtrack search, but it really is sort of a brute force search strategy. Okay, so under this we will be looking at what is called backtrack search. Then we will look at a strategy called branch and bound. We will also be looking at a strategy called dynamic programming. And in fact, it is this strategy that we want to study the most, because this is a strategy which we can analyze, and very often it gives us very fast algorithms as well. But it requires us a considerable amount of clever analysis. But I want to start talking about this strategy today. There is also a strategy which is often called the greedy strategy, which is also going to be discussed in this course, because this also gives us very fast algorithms for solving combinatorial optimization problems. Let me point out right away that this strategy, the backtrack search strategy, is probably the most general. This can be applied to almost any problem. This is a more restricted strategy, but it becomes a little bit more efficient than backtrack search strategies. Okay. Dynamic programming typically is more efficient than branch and bound, but it requires us to do a lot more analytical work. Okay, we need to actually exploit the problem, and it's not always the case that dynamic programming ideas will be applicable. So let's come to brute force search strategies. the name should suggest to you that we are going to do something fairly simple-minded. And in fact, let us just sketch how we might do this simple-minded. We might do something simple-minded to make sure, however, that we do get an answer correctly. Okay. So the basic idea, as you might guess, or as the name suggests, is to systematically somehow enumerate or generate all possible objects which can potentially satisfy the constraints. Okay. For each object, here is what we do. Well, we first check whether in fact the constraints are satisfied. If so, we evaluate the cost or benefit function. If the cost is better than the cost found so far, that is, if the cost of this object is less than the cost of the best object so far, found so far, then we store it. So we record cost if necessary. Similarly, if there is a benefit function given to us instead of the cost function, we evaluate the benefit function and check this benefit function with the best benefit function found so far. If this new object has a benefit function which is better than the best benefit function found so far, then we record this benefit function and also the current object. Record cost if necessary and current object. So clearly, if we generate all possible objects and we check whether each of them satisfies the conditions, this procedure must certainly work. Okay, this procedure will be guaranteed to give us the correct answer. Okay, just because we are just going over, we are doing everything that can possibly have to be done. A question, however, is how do we systematically generate all possible objects? And that's where a slight amount of cleverness comes in. So generating all possible objects, or how to generate. The basic idea is, think of the object that we want as a collection of parts or a collection of slots. Then consider each possible way of generating each part, or if you want to think of this object as a template in which there are slots to be filled, we want to think of each possible way of filling each slot. How do we go about actually doing this? Well, we go over the parts or the slots one after another. So the basic idea is that initially we sort of have an empty template. Okay, so all slots are empty. Then we fill in the first slot. Of course, this can be done in several possible ways. So here we have to consider all the alternatives, then we fill in the next slot, and again we consider all the alternatives over here, and so on. Okay. Let's take an example, and that will make this idea very clear. So let's take the example of 8 queens, but since this page is small, let's just make it 4 queens. Okay. So what do we have? Well, we have variables q of 1, q of 2, q of 3, and q of 4. So we can think of these 4 as the smaller parts comprising our big object that we need to find. Okay. Or we can think of this as a template with 4 slots in it, which is given to us, and we want to fill in values into the slots. Instead of looking at these numbers themselves, I'm going to think of this, I'm going to interpret these numbers and pictorially draw the board that corresponds to this. So initially we are going to start off with an empty template. Okay. So that corresponds to a board which is completely empty. Then we are going to consider the ways in which the first slot in this template can be filled. So Q1, we said, must have a value between 1 and n, where n is 4 over here. Okay. And so there are 4 ways in which this can be done. Okay. So for example, something like this. So we can place the first queen in this first position over here. But this is not the only way in which this slot can be filled. There are many other ways in which this slot can be filled as well. And so here is another. So from this empty template, we can come to this way, this possible way of filling the first slot. That is, we place the first queen in the second row. Okay. Of course, it's not necessary that we place it in the second row, but we might place it in the third row as well. Okay, so this is that corresponding position, and of course we can place it in the fourth row. Okay, I'm not drawing the entire board, but I'm just telling you where the queen is going to be placed. So these are all possible ways in which the first queen can be placed, and we started off with the empty board, and at the end of considering how the first slot can be filled, we have arrived at 4 possible positions, okay, or 4 possible candidate objects, each of which is only partially built. So we started off with 1 partially built object, candidate object, and now we have 4 partially built candidate objects, but they have been extended. So we started off with this object, and these are objects which are fuller in some sense, or more built up than this previous object. But we can keep going in this manner. So from this point, we will again consider all possible ways of placing the second queen. The first queen is placed over here. The second queen could also be placed in the same row, okay, or it could be placed in the next row, okay, or the row after that. Okay. Or finally in the last row. So when we come down to this level, we have our object even more fully constructed. So we have placed 2 queens. We have not placed all of them yet, but this is at a higher level of construction, higher level of completion than this one, which in turn is at a higher level of completion than this one. And of course, each of these objects will have to be constructed further. Okay. So there will be something over here underneath everything which represents the ways of placing the third queen, and then underneath this there will be something which represents the ways of placing the fourth queen. Okay. In this case, we can see what's going to happen. So we started off with 1 node, then we have 4 nodes. We have 4 boards in this next level. Okay. Then we have 4 squared boards to be considered at this level, 4 squared partially constructed objects. Then we have 4 cube partially constructed objects at the next level, 4 times as many as the one in the previous level, and finally 4 to the 4 objects at the leaf level. In fact, I have already told you what this looks like. in some sense. So we have leaves at the bottom, we have a root at the top, and in fact this is going to look like a tree. In fact, in almost every in exhaustive generation method, we will be following something like this. So we start off with the empty object, we keep on extending it. So the extension will correspond to children of the parent node. Their extensions will correspond to objects which are even fuller, and until we get to a point at which we cannot extend the object any further. That is the point at which we have got to leaves, and that is the point at which we can terminate our generation step. Once we get to a leaf, in this case, for example, we know that we have all the queens completely placed. So what's the next step? Well, at this point, we are going to check if the queen positions satisfy our conditions. If they do, then in this case, we can just report, we can just print out saying, yes, they do in fact satisfy all the conditions. If they don't, well, then we have to consider the other leaves. Okay. This is as far as considering problems in which there is no objective function. If there is an objective function, then when we get down to this level, we need to not only consider whether the leaf objects satisfy the constraints, but we also need to evaluate the cost function. So suppose in fact we have a cost function rather than a benefit function, then for each leaf we can think of the cost function, and we can evaluate the cost function, and our problem is to find a leaf such that it satisfies all the constraints and such that whose cost function is as small as possible. So let me sort of summarize what I just said in terms of a programming idea. Okay, so first we need something so that we represent our objects properly. So for example, in the case of the 8 queens problem or a 4 queens problem, we used a data structure of an array, a 4-element array to represent the 4 queen positions. In case of the traveling salesman problem or the traveling salesperson problem, we want to represent a tour. Again, if the graph has n vertices, we could use an array of length n, where the ith element of the array denotes the ith city in the tour. In the case of the knapsack problem, we simply need to say whether a certain object has been selected or not. So corresponding to each object, we could have a bit which is equal to 0, meaning that object is not to be placed in the knapsack, or if that bit is 1, then the object is to be placed in the knapsack. So somehow or the other, we need to have a representation of the object that we are looking for. After that, we need a procedure for filling in the next empty slot in the object. Of course, there will be many ways in which this can be done, and so this procedure should allow us to provide all possible ways. Okay. At this point in the algorithm, we are simply going to recurse. Okay. So then we will recurse, and we will recursively fill in the subsequent slots. What happens next? When we have recursed, it is equivalent to starting at, say, the root, and we filled in the first slot, and then when we recurse, we filled in the next slot, and so on. Eventually, we will hit the leaves. Okay. So we really need to have a check over here just to see whether we have hit the leaves. Okay. So for leaf objects, we need a procedure that checks constraints. and it returns true if all constraints are met. It returns false if the constraints are not met. We also need a procedure for evaluating costs. That is not all, however. So this way we keep going down and we go down to a leaf. But we also want to go back up and go to the other leaves. And that is why this whole procedure is called a backtrack search. So we get to the leaf, and then we go back up again in the tree, and then we go to the next leaf. Then from that leaf we go back up again. And so over here we said that we need a procedure for filling in the next empty slot in the object. But similarly, we need a procedure for removing the last value filled in the last slot. This is how we will go back up into the tree and make sure that all the objects will get generated. So let me try to write this as a very vaguely as a procedure, just to give you the idea of what is going on. So our search procedure is going to look something like this. So it's going to take this candidate object as an argument, and let me just note that this, while I have written an object over here, I really mean this template, which could be partially filled. So what does this do? So if object has all slots filled, which is to say that it is a leaf, then we are going to check constraints. We are going to evaluate the objective function. Okay. If constraints satisfied, and in fact we will return the value. If the constraints are not satisfied, we will return. So if the constraints are not satisfied, then we will return infinity if we are given a cost function. Okay, that is to say that this leaf found is to be disregarded. Okay. Infinity will just say that this is a useless leaf. Okay. If we will return a minus infinity or a 0 if this is a benefit function. Assuming that the benefit is positive, we can even return a 0. Okay. So this is what we do at a leaf. Okay. If object has unfilled slots, then what do we need to do? Well, we need to do this branching business, right? So this has unfilled slots, so we need to fill further slots. If object has unfilled slots, okay, we are going to consider all possible ways of filling slots, filling next slot. Okay. So we will fill in ith possible manner. We will recurse. Okay, so we will recurse on modified object, and this recursion will give us a value. So let me call this v sub I. Okay, and this will be the end of the loop. Okay, so think of this, consider as being a loop, loop. And now the idea is something like this. So we are going to go over all possible leaves, okay, underneath. So starting at this, we will be visiting this, we'll be visiting this, we'll be visiting this, we'll be visiting this, and we are going to associate with this node a cost function, which is the value of the smallest cost function found anywhere over here. That way we can return that, and eventually we'll make sure that the smallest cost gets returned to the top. So here we are going to be returning smallest v sub I calculated above. Okay. So let me do this again. So we start off with an empty object, then we consider all possible ways of doing it, but really in the first instance we just go along this path, then we go along this path, then we go along this path, and so on until we get to a leaf. Say, let's say we get to a leaf over here. Then we return the value of the cost as seen at this leaf. Okay. Then at this point we consider other ways of generating it, and we get to another leaf, for example. Then we return this cost, then we go back again, then we return the cost over here, and let's say there are no more ways of filling in that last slot. Then at that point what gets returned over here is the smallest of these cost values. So in general, in this manner, what's going to get returned to the root is going to be the value generated along some path in this graph, and that's going to be the least cost leaf, the value of the least cost leaf. So this completes a description of this search procedure. In fact, if you have studied this in the data structures course, what we have done really is a depth first search over the search space. Search space is simply set of leaves. Okay. We want to look at all the leaves somehow or the other, and so that's often called a search space. And what we are doing is we are putting a tree on top of that search space, and we are just doing a depth first search of it. There are some improvements possible to this procedure. We don't need to do our conditional checks, our constraint checks at the very end. We can do them as early as possible. So for example, in case of the 4 queens problem, suppose we place the first queen in this first row. Then when we place the second queen in the first row as well, we could say, look, these 2 queens already are capturing each other. Okay. Or the condition that q of 1 equals q of 2 not equal to q of 2 is not being met. And therefore we can say we don't really need to go and further check where queens 3 and 4 ought to be placed. So what happened over here was that we started off with the empty board, then we placed the first queen, and then we placed the second queen as well, and then we can say we can safely ignore this part of the search tree immediately. Okay, because we are checking the condition right here, and this condition which we check should be something which will be valid no matter what leaf we get to over here, and in fact that is true. These 2 queens are not going to change their position at any of these leaves. At these leaves, only these queens will get placed, and therefore this condition will stay as it is. Okay. So the possibility of early condition checks can improve upon the efficiency. I would also like to note that this procedure is obviously correct, and that really follows from the fact that we are considering all possible ways of filling each slot. Let me go to our second example, which is the traveling salesperson. Okay. So I'm just going to give a quick description of what this search tree is going to look like. So at the root, we are going to have the empty tour. So let's say this is our graph. Okay. Then we can say that let's designate this vertex as the starting vertex. It doesn't really matter since we are going to come back to this vertex anyway, since the tour is cyclic. Okay. But suppose this is the starting vertex, then we can ask how many ways are there in which the tour can go out of this vertex, and that gives us, that sort of fills in the first slot in the tour. So for example, we can come to this point at which the tour has proceeded along this edge, or we can come to this point at which the tour has proceeded down diagonally, or we can come to this point at which the tour has gone down. Then this tour can further be extended over here. So starting at this, it can go down directly, okay, or it can go back diagonally, and so on. So eventually we'll get to a leaf where we'll be having complete tours. So let me say something about the running time of backtrack search. Okay. So basically the idea is that we are going to look at every possible leaf. So the time taken will essentially have to be, at least in the worst case, have to be the number of leaves. So let's consider this for the case of the n queens problem. Okay, so let's generalize it to n queens rather than 8 queens or 4 queens. So in this case, how many leaves do we have? Well, the first queen can be placed in n ways, the second can be placed in n ways, and so on. And so there are n to the power n leaves, and so time is at least n to the power n. If you implement the early checks, then the early checks will improve the situation somewhat. And in fact, a very simple early check is to say, let me make sure that this new queen is placed in a different row from all the previous queens. Okay, so here our output will simply be a permutation of the numbers 1 through n, and so here there will be n factorial leaves. Okay, so the time is going to be omega of n factorial. This is still quite large. What about the TSP? How many tours do you have through n cities? Okay. Well, starting at any city, the first city can be picked in n minus 1 factorial ways, then n minus 1 ways, then the next in n minus 2 ways, and so on. And therefore, we will have n minus 1 factorial different leaves in this search space. So simply put, there are 3 ways of getting to the vertex at the first level. The next, there are 2 children, and in this case, there will be 1 child, and so on. But in general, if we start with an n city tour, there will be n minus 1 children at the first level, n minus 2 children at the second level for each of the vertices in the previous level. So therefore, we'll have n minus 1 different leaves, and again, here the time will be omega of n factorial. For the knapsack problem, it should be possible for you to prove that there will be 2 to the n leaves corresponding to all possible ways of forming subsets of n objects. So let me summarize this whole situation. Okay. So what have we done so far? We have looked at a very general method. It is brute force. It is brute force in that it generates every possible object, and it doesn't try to be too efficient or too clever in saying, look, I'm not going to generate this class of objects because this is not going to be useful to me. Okay? And typically, it takes a long time. Okay, in fact, typically it takes time exponential in the size of the object. So either 2 to the n or n factorial or n to the n or something like that. And we have defined terms like search space and the tree that sits on it as the search tree. And let me end this lecture by mentioning one more term, which is combinatorial explosion. This term is commonly used in connection with backtrack search. The idea is that at the first level, the tree might look manageable because it has a small number of children. At the second level, the number of children, the grandchildren of the root will grow. At the third level, the number of children will grow further. And eventually, when you get to the leaves, you will have many, many, many children or many, many, many vertices. And so in some sense, your tree will explode. And this phenomena is commonly called combinatorial explosion. So let me just look at what we are going to do next. Okay. We are going to study improvements to backtrack search. Okay. As mentioned before, we are going to study a technique called branch and bound. And then we will look at dynamic programming and greedy strategies. And this is really the focus of this course, but it is important to view these as a part of a grand picture in which sort of the simplest backtrack search ideas are present, as well as these more sophisticated strategies are present. You should also note that the backtrack search is a very, very general strategy, whereas these are very, very sophisticated but very specialized strategies. These are likely to be fast, as you will see in the next lectures. This is likely to be slow, but it is going to be very, very general and applicable in almost any combinatorial optimization problem.